Okay. So, sadly, it's not cold enough to have a day off. And I toyed with the idea of just having you watch the video, but this stuff is kind of intricate, so I will put the video up if you want to go back and watch it. So today what we need to talk about is we need to talk about the peaks in the NMR spectrum, the x-axis, what does it mean? What if the peak is in a certain part of the spectrum, sort of like what we talked about with IR, how we get that. And then there's some other complications to NMR that, while it's more complicated, it gives us a ton more of information. So last week at the end, I showed you a little bit about MRI, but then I spent a little bit of time talking about the different sizes of magnets that these instruments operate under. Maybe a little longer than I should have, but we're gonna kind of get back to that today. So what we want to do is we want to look at the differences in the proton peaks. Why do they have different peaks, and then how do we correlate that onto the x-axis? So that's going to take a little bit of building up here. And the best way for me to explain that is to not use our current method of collecting an NMR spectrum, but to actually talk about the old way. So what's the old way, what's the new way? So here is sort of a colorized version of what we saw last week. And this is the older methodology for collecting an NMR spectrum, what's called non-Fourier transform, the non-Fourier transform mathematical method. What Fourier transform mathematics does is it will take basically a collection of frequencies and it'll tease out the individual frequencies. So one of the ways we can do the experiment is the old-fashioned way, which is we basically take and we could hit it with a frequency, then scale up a frequency, or scan through the frequencies. And once we hit the frequency where the nuclei, remember, are precessing, the nucleus flips its spin, and we get the peak. Bless you. Might as well wait till you're done. So that's one way to do the experiment. It takes a long time to scan through them. The analogy is the equivalent of playing the piano by pushing down each key going up the keyboard. The other way is to use Fourier transform mathematics, which means that I hit the sample with a collection of pulses, and then I let the math tell me what frequencies were there and what weren't there. So that would be the equivalent of slamming your arm down on the piano and then having math tell you which keys you pushed. And that's actually, this is how we do the experiment now, for reasons we'll talk about. So in the non-Fourier transform instrument, what we have is we have a constant radio frequency being applied to the pulse, or applied to the nuclei. And then, because these are electromagnets, we can change the current going through the magnet and change the magnetic field. So what we're doing is we're basically going to change each nucleus's radio frequency by changing the magnetic field. Because if we apply a faster or a bigger magnetic field, it will spin. Well, it's already spinning at a certain precessional frequency. But I can change that and put it into what's called resonance with the radio frequency. And so we'll come back to that, because what I'm doing is I'm changing the magnetic field. In the new instruments, I have a magnetic field that's constant, and I'm applying different radio frequencies. I literally am smashing the keyboard and then letting the math tell me what peaks were present and what peaks weren't. And the advantage of that is that that takes a few seconds. So what I can do is I can hit the sample with a pulse and then figure it out. Another pulse, and what happens is if I have dilute samples, I can basically take like thousands of scans. Whereas over here, if I have a very small signal, I need to take a scan, take another scan, and add up the spectrum. Peaks will constantly reinforce themselves, random noise will end up at 0. So for really dilute samples, I need to take multiple scans. This, not good way, this is a better way. But there's two completely different. So I've got a constant magnetic field. I'm going to apply a wide sweep of frequency and then use Fourier transform math. Basically what it looks like is we get a free induction decay of the signal, basically becoming less and less over time. And Fourier transform mathematics takes that, so there's your frequency. Or multiple frequencies. I'm going to talk about this. Yeah.
Is that mathematics like taking that cone and then just flipping it upright?
No, it's basically figuring out in the free induction decay what frequency this corresponds to. But this is a real simple one because this is just a single peak. We might have 30 peaks. And so this becomes basically a solid block of signal.
Okay.
So that's how we can do it, is through that free induction decay. And then if you have that, you can do other things with it. We're not going to really talk about that. We'll talk about the idea that I need scans. So I need, a second, 100 seconds, I can collect 100 scans. So we're going to talk about this. So how do the nuclei have different frequencies is the question. And so if that's the way we're going to discuss this, which is the non-Fourier transform method, then I need to know why on this x-axis peaks show up differently, which peaks show up where. This is a correlation chart. So it's going to tell me the hydrogens attached to benzene rings show up between 7 and 8. I got to answer the question 7 and 8 what? What does that correspond to? And then why they show up in their different places. We also need to know what upfield and downfield is, and what deshielded and what shielded is. And then we also need to know high field, low field on the spectrum. So that's what I'm going to work my way to. Okay, so first of all, what is the unit on the x-axis? The unit on the x-axis is what's called delta. It's called the chemical shift, and it's in parts per million, ppm. So we'll work our way through that. So the chemical shift or position of a proton is dependent on its magnetic field. Or remember, its Larmor frequency. And we're going to talk about this in terms of magnetic field, not necessarily Larmor frequency. There is a direct relationship between the applied magnetic field, and the nucleus's Larmor frequency. We talked about that last week, or I talked about it last week. The idea that if you have a 7 Tesla magnet like we have next door, protons spin at 300 megahertz. If I go to a 20 megahertz or 20 Tesla magnet, they're going to spin 3 times faster. So the applied field and the Larmor frequency, there's a direct relationship. Stronger field, they spin faster. But that's the applied magnetic field. Remember, a little nucleus that's spinning, a spinning positive charge, is its own magnet. So what's its own strength? Its own magnetic field strength is inversely proportional to the Larmor frequency. So the faster it spins, the smaller it is as a magnetic field. And the slower it spins, the larger it is. So that's what we're going to talk about. The idea that each nucleus is its own magnet and has its own strength. And if it has its own strength, it's going to show up in different positions on this spectrum. So this is sort of the different areas of the spectrum. For instance, if these chemical shifts increase as we go from right to left, so this is the high chemical shift field end, this is the low chemical shift field end. We'll talk about shielding and deshielding and shielding. This is the high frequency end, this is the low frequency end, so as I go from right to left, the frequency of the nucleus is increasing. And then if I looked at its magnetic field, the magnetic field is just the opposite. So where it says high frequency, low frequency, this is the low magnetic fields and then this is the high magnetic field end. So they're opposite. So as frequency increases from right to left, magnetic field strength. In other words, the size of that nucleus, its field strength decreases. And then going from left to right, it increases. Okay. And then there's something called upfield and downfield. And then you don't have to worry about towers. Nobody's used a tau in like 40 years. So it's just it was related to chemical shift back in the day. It would be like 10 minus the chemical shift, but again, nobody uses it. So that's, I don't know why some are happy and some are sad. I didn't figure that out. But this is the way the spectrum works. This is going to be this side, and then this is going to be the other side. So what we're interested in is we're going to be interested in the field. So as we go from right to left, we're going to a lower magnetic field. That nucleus is becoming a weaker magnet itself. And that's how we're going to explain this. I'm going to try and explain this. All right, so where does this come from? What affects the magnetic field strength? Is the first question. Well, what affects the magnetic field strength of the nucleus, how strong it is as a magnet, is the electron clouds that surround it. Most hydrogens are attached to carbon, and so the electron clouds belong to carbon. But if I can change the electron clouds or the density around that carbon, I'm going to change the position of the hydrogen on that spectrum. And so it's the hydrogen, but it's also the carbon that's really the important thing here. And that's going to be affected by polarity, hybridization, and whether we have electron donating or withdrawing groups. So here's what I have to imagine. Here's my nucleus. So I'm the nucleus spinning around. And I have a certain magnetic field strength. And what will happen is that if the big magnet, and I'm doing this in the old days, so in other words, I'm changing the current and changing the magnetic field strength of the electromagnet. When that magnetic field strength equals me, then I absorb the radio frequency that's being used in the instrument, and I flip my spin. So if I'm like 10 units, and that thing's applying 9, I can't absorb the radio frequency. As soon as it hits 10, I absorb the radio frequency, I flip, we see a peak. So that's what's called being in resonance. You're in resonance when you as the little magnet proton nucleus have the same field strength as what's being applied. Okay, so this is the old system where I'm changing the current and changing the magnetic field strength. But it's still the radio frequency that's making me flip. Right? So that's when I as a nucleus come into resonance. Is when that applied field equals me. Now, that if I was just a naked proton out in the gas phase with no electron clouds around me, everything would be great. But if I'm attached to a carbon, now I've got these electron clouds. What do they do? Well, the electron clouds, or the electrons, they orient themselves so that they're like perpendicular to the field. And then there's this right-hand rule thing with physics, so that they decide to rotate this way, so that they create, my thumb, they create a field going down. So the electrons spin around and create a field that is opposite me and the applied field. And so what happens is that when I'm the nucleus, I see an effective field. And my effective field is going to be whatever the instrument is applying minus the field that the electrons produce. And the more electrons that there are, the more this field, the bigger it is numerically, the bigger negative it is, let's say. So the field strength, the field of the electrons subtracts away from the applied field. So the way this works is I'm at 10. The nucleus, or the applied field over there is 10. But let's say the electrons in between are at -3. So if I'm at 10 here, my electrons are producing a -3, and I decide to apply a 10 for my magnetic field. Am I going to be in resonance? Am I going to have exactly the same field? No, because what do I see coming at me? 7. So unless I see 10, I'm not going to flip my spin. So what does my applied field have to be? 13. So in other words, I have to increase my applied field to 13 in order to overcome the 3 of the electrons. Now I see 10, I'm 10, I flip. That seems simple enough. And basically it is. Because what this is telling me is that the more electrons that we have surrounding the nucleus, I'm going to say that those electrons shield the nucleus from the applied magnetic field. And that's what they're doing. By providing a field that's in opposite direction, they're shielding me from the applied nucleus, or from the applied field. So the more electrons I have, the applied field. If I increase the number, if I increase the number of electrons, or I increase the electron density, what's going to happen to the field? I'm going to have to increase it. Right? So the more electrons, then I'm going to have to increase my field, my applied field, in order to make the nucleus come into resonance. And again, this is the old instrument where I can dial in the current and change the magnetic field. So when you have more more electrons, that's called shielding. And the more shielding you have, the higher your magnetic field has to be to bring the nucleus into resonance. Everybody with me? I'll try. And the shielding and deshielding and the upfield, downfield stuff, hopefully I'll get it all right today. But this is one of those things, like sometimes if I have to go to parts per million to parts per trillion, I lose a decimal point along the way. I taught an entire class backwards one time. Sadly, it was when one of my colleagues was observing. And somebody at the end goes, "Don't you have this backwards?" And I go, "Oh yeah." But see, I was illustrating how it's tough to try to figure it out. Didn't work. So there's a possibility I might get this backwards. But so far, I don't think so. Right? So more electrons, more shielding requires more field. So let's go back. Okay, so let's go here. So what does that mean? If we go back to our little chart here, where I said that basically to the left is the low field end, and to the right is the high field end. You can see we've got basically less shielding and more shielding. We sometimes call the less shielding de-shielding, which probably is what screws me up because we normally don't talk about more of less, which is in essence what we're doing when we talk about there's more or less shield or less shielding. So when I shield, when I put more electrons in, that peak is going to occur more to the right, more to the right-hand side of the spectrum. When I have less electrons, then I have less de-shielding or less shielding, which means that I don't have to apply that much over the field, and so then I have what's called the lower field to the left. So that's what happens when you have less shielding. So on my spectrum here, how does that happen? How do we get shielding and de-shielding? And so here's an example. And my example here is, I'm going to start with methane. We all know that methane has the hydrogens being delta plus, and that makes the carbon slightly negative. So what is happening there? If the hydrogens are giving, or if the carbon is getting more electron density, it's becoming shielded or de-shielded. More shielded. So it's going to be shielded. So if it's more shielded, that means it should be at a higher magnetic field. I have to apply a higher magnetic field to make this system come into resonance. And so that peak should be on the right-hand side of the spectrum. Okay, so it's in the high field side. And it's what's also called upfield. Added chlorine to it. What's the chlorine do? In terms of a polar covalent bond. What does the chlorine do to the carbon? It's going to pull electron density out. So the chlorine is going to become delta minus, and the hydrogen is going to become delta plus. Remember, as a hydrogen, I don't really have a lot of electron clouds. So the electron clouds that surround me are the same ones that are surrounding the carbon. So what has the chlorine done to the proton and the carbon. By pulling electrons out, it has caused less shielding. It's caused less shielding. And so that means I don't have to apply that much more extra field to bring me, the nucleus, into resonance. And so that means that I have a lower applied field. And my lower applied field then causes the peak to move then to the left.
So if there was a carbon attached to the 3H carbon instead of a chlorine, would the peak be in the middle of the two?
Well, we'll come to that.
Okay.
So if we have multiple carbons here, the one that's closest to the chlorine is going to be the farthest left. And then what you're going to see is, as we move away from the chlorine, the peaks will move to the right. So this is then less shielded, and the peak moves then to the left. It moves to a lower field. Again, because there's a reverse relationship, it's spin fast. Lower field for me as a nucleus means I spin fast. I have a higher frequency. Two chlorines, what happens? Even more shielding. See, I did it. Even less shielding. Or more de-shielding. We'll just say less shielding. So two chlorines, less shielding. Magnetic field is lower. Peak moves to the left. And then less shielding. And then three chlorines, even more, less shielding, lower still magnetic field, peak continues to move to the left. I go one more chlorine so that I have carbon tetrachloride. No signal, because I have no hydrogen to determine the signal of it. So each time I'm looking at the hydrogens that are attached to the carbon. So the electron density around the carbon is what's going to affect the electron density of the hydrogens, because that's who they're attached to. So to the left, less shielding. To the right, more shielding. And our situation is going to be most of our molecules are actually, most of the peaks are going to occur to the left of what we're going to call zero here. So most of our molecules are actually de-shielded to some extent. Only when I start pushing electron density into the carbon am I going to truly see a shielded event.
Is there a peak on an amine hydrogen or a hydroxyl group hydrogen?
Yes, and we're going to come to those. But when you have H's attached to N and OH, they can show up anywhere between 0 and like 14. For reasons that we'll get into. Only the hydrogens that are attached to carbons are going to be in our correlation chart. The OHs and NHs, some of those will be on the correlation chart, but they're varied. They can show up between like 0 and literally 14. When I was in graduate school, I asked the guy ahead of me, so where do you think this will show up? And he said between 0 and 12. And I said, can you be a little less helpful? Because that's the scale. It doesn't get any bigger than 0 to 12. Okay. So the initial question was, how do the peaks show up at different positions? They show up at different positions because the carbons they're attached to are being shielded or de-shielded a little bit differently. And this is small. This is an incredibly small effect, but it can be easily measured in proton NMR. Is everybody still kind of with me? Okay. So then there's our spectrum. So quick quiz. High field, low field. Okay, so this is the low field end. High frequency, low frequency. High frequency, because frequency and the frequency of the nucleus and its strength as a magnetic field are opposite, inverse. So that means over here, this is my high field end, and this is my low frequency end. De-shielding or less shielding or more shielding? To the left. Less shielding or de-shielding? Everybody uses the de-shielding term. Well, like I said, maybe it's just easier to say it's less shielding. To the right, more shielded. And what does that mean? More electron density on the carbon that the hydrogen is attached to. And then we won't use this term necessarily a lot, but this is my upfield and this is my downfield end. Okay. So that's how the protons get different peaks on the scale, and that's what makes them shift, either to the right or to the left. Basically, we're really talking about all of these things shifting to the left. Everybody okay so far? You could be home watching this at 1.5 times speed, just blowing through it, but if you really wanted to get it, you'd have to watch it multiple times. I would think probably slower and slower. So, the x-axis, what is it? So what are the units for the x-axis? Well, we're measuring the x-axis in hertz. But I haven't come up with a way yet, maybe somebody else has, to explain this whole shielding and de-shielding deal using the Larmor frequency. But I haven't yet been able to do that at this level. So remember that when we're talking about high or low field, the frequency is the opposite. Right, so while the overall Larmor frequency is in the 300 megahertz region in our magnet next door, the differences between those peaks is anywhere between 100 to maybe 400 or 500 hertz. So the peaks are spinning at 300 point blah 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 hertz, and so the differences between the hydrogens, between the proton peaks, are 100 hertz or less. But we have to keep in mind what the overall core, the big frequency is, and it's in the megahertz, 300 megahertz. So first thing is I need a zero. So what I'm going to do is I'm going to choose a compound that's going to give me a peak that I'm going to set to 0. In the old days, I used to have to move the pen because the pen would like go across the paper and draw. So I'd have to set up the pen so with that compound it would be right at 0. So what we choose is tetramethylsilane, or TMS. So in TMS, I've got a silicon attached to 4 methyl groups. What does the silicon do to the carbon? Silicon is less electronegative than carbon. So does it donate? Does it withdraw? If silicon is silicon is less electronegative than carbon, who's going to get the electron? The carbon. So the carbon's going to become slightly negative at the expense of the silicon, which is going to become slightly positive. What did I just do to the carbon and the protons? By making them slightly negative. I have shielded them. So where should that peak occur? To the right. And this compound is so shielded that nearly everything else occurs to the left of it, which is another ideal standard. You don't want your standard in the middle of the spectrum. So this way I only have positive chemical shifts. I don't have to worry about positive and negative ones. There is on occasion a peak that will show up past the 0, but we're not really going to get into those. So for the most part, everything is to the left of this. Okay, so there's my 0, tetramethylsilane. The reason we also choose tetramethylsilane is if I had a reference to my compound, I want to get rid of it. And TMS has a boiling point of 28 degrees. I think the inorganic class was saying, where's the TMS? Number one, I'm not teaching an organic class or lab, so you should be asking your instructor. But number two, I have no idea. Number three, how much should we add? As little as possible. So I'm like, take a pipette, stick it in, and take up the vapor, and shoot the vapor into the food. Because it boils so low, I could basically evaporate it off of my sample so that I don't want to add something that I'm never going to get rid of. And secondly, with 12 hydrogens, if I had too much, I see this huge TMS peak, like little tiny sample peaks. So I want to add a small amount as possible. Right? So then you can add TMS to the sample, set that proton peak to 0, and measure the frequency of our sample peaks relative to that. And so that's what we do. Except, here's a problem. What happens when I change the field strength of the applied magnetic field? In other words, when I go to a stronger magnet. So last week I talked about, well, the peaks would be like this if it was 300, but then the peaks would be like this if it was 900. Because the peak frequency is going to be proportional to the applied field. So if I go to a 3 times stronger magnet, I'm going to get 3 times the number of hertz. So basically, what does that mean? Does that mean that, every time I get a new magnetic field strength, I've got to come up with a new correlation chart because I got to change the x-axis numbers? Or do I just have a whole collection of these and I just choose the one that's appropriate for my instrument? Neither one of those is really good. So, in 1945, Bloch and Purcell were the first people to come up with NMR, to record NMRs. These are their NMRs. We'll see better. That's what I'm getting right now in my instrument, because it's thick. It's going to require an infusion of cash to fix it. But at least I know what the problem is. That's better than not knowing what the problem is. So they measured wax and ethyl alcohol. 1945. So we haven't had NMR since basically like the 50s. And The little tabletop NMR that I showed you, that was state of the art through the 60s. And then people got better and better as they could get stronger and stronger electromagnets. Then when we entered superconducting phase, where you now have materials that are bathed in liquid helium that have super high currents and super high fields, now we have the modern day instruments. So Bloch and Purcell were the ones that did that. Then later on, they discovered chemical shifts, which is what we're talking about. I would have given these guys the Nobel Prize for how they handled chemical shifts, because they thought 50 years in the future when they decided how to define the x-axis. And they both won the Nobel Prize. But like I said, I would have given them the Nobel Prize just for how they handled this. So my problem is that if I have two peaks at if I have two peaks, and let's say one peak was at a relative position of 0 hertz, and another peak's at 100 hertz, on a 300 megahertz magnet like what we have here, if I then take that sample down the case and I measure the peaks in hertz, this one's going to be 300 hertz, and this one I'm still setting at 0 hertz. So as the field got stronger by 3 times, the hertz peak position got 3 times bigger. And again, maybe this isn't true, but I'll give these guys credit. They thought about what happens if we have stronger magnets in the future. I don't want to come up with a correlation chart and then have to throw it away every time I get a new magnet. So what they decided to do was this. They defined the chemical shift as the difference between the peak that I'm looking at and the reference peak frequency. That's what the nu stands for, is frequency, divided by the operating frequency of the NMR in the hundreds of megahertz or whatever it is. So if you do that, you say, okay, the chemical shift then, which is delta, for this one is equal to 100 minus 0 over 300 megahertz. So I've got hertz over megahertz, and so that would be 100 over 3, which means that peak would show up at 0.33 on the scale. If I now go to a 3 times stronger magnet, I now have 300 minus 0 hertz over an operating frequency of 900 megahertz, which is 0.33. So by coming up with a reference that you set at 0, by measuring the frequency relative to that, by then dividing through by the operating frequency of the instrument, you get basically a dimensionless x-axis, so that the numbers will never change. And like I said, I think, if there's ever, examples of just being super genius, that's it. Because to anticipate that we would have 900 megahertz instruments back in 1950, the materials weren't even made yet. There might have been theoretical knowing about superconducting materials, but they hadn't been made. Let alone to be able to liquefy nitrogen and helium in order to be able to use in our current instruments. So they came up with a scale that will never change. That scale then is delta, the chemical shift. I am measuring a hertz out of a million hertz. And so that's where the 0.33 part per million scale comes into play. And those of you that are taking analytical or have taken analytical, you know that a part per million is basically a gram out of a million grams, or more likely a milligram, 10 to the minus third grams, out of a kilogram, So when you're measuring units of part per million, you're normally measuring like a milligram in like a liter of water. It's a milligram of stuff in a kilogram of water. So that's 10 to the minus third divided by 10 to the plus third, or 1 over 10 to the 6. So now I have a shift, I have an x-axis independent of the magnetic field. There are some issues with magnetic field strength that'll make the spectrum look different, but we'll get to that. So that's what the x-axis is about. So I can make a correlation table. And so here's my correlation table. What I usually find is the peaks that are farthest to the right are always methyls. If my sample has methyl protons, has a methyl group, they're always the farthest to the right. They're the last peak on the right. Then if I start adding electronegative elements to the carbon with the hydrogen, like a nitrogen, like a sulfur, like put it next to a C double bond O, now all of a sudden I'm shifting to the left or going with less shielding. If I attach a halogen or an oxygen, my peaks are going to show up between 3 and 4 because again they're becoming less shielded. These ones, that idea of shielding and de-shielding, it doesn't quite work in the way that we're thinking about. Here, with the oxygen, so the oxygen is delta minus, making the carbon delta plus, and what have I done? I've de-shielded or I've made the carbon less shielded. Usually don't put this in, but I decided yesterday as I was going and revising my notes, I would just show you. How does a hydrogen attached to a benzene ring show up at 7? Well, when you look at a benzene ring, and we'll do this, we're not quite to that in lecture yet. But when we look at a benzene ring, because we've got 3 double bonds, we've got then the p orbitals that are overlapping to form basically a continuous like donut of electron density. Well, if you think about that, those electrons and those movements, we then end up with a situation where we end up with the physics right-hand rule. In the magnetic field, those electrons will be perpendicular and they will circle around, creating a field that is down. So in the center of the benzene ring, the field is opposed. And it's shielded. So if you put a hydrogen at the middle of the benzene ring, which you cannot do, but if you could, that hydrogen would be shielded to be to the right. When you draw out the magnetic lines of force, they go down, then they come back up again. Where's the hydrogen attached to the benzene ring? On the outside, where now the field is the same as the applied field. And so those hydrogens become de-shielded. Then they shift all the way to the left as 7. So what we're going to see is if we see peaks between 7 and 8, we're going to say benzene ring. No question. Peaks between 7 and 8 are going to be benzene ring hydrogens. When I talked about IR, we could get a sense of whether there might be a benzene ring there. When I take the proton, those peaks of 7 tell me automatically there's a benzene ring. And I was going to include the picture of our friend porphyrin ring from Organic 1 in the spinach lab, right, where we had the magnesium sitting in that big ring. Well, it turns out that those hydrogens that are on the inside of that ring It does the same thing here, only now those hydrogens are in the middle, and they're now very shielded. And they actually show up above zero, which is the negative chemical shift. So if I took a porphyrin ring and I determined its proton spectrum, that's one of the cases where I would see a peak that it's a negative chemical shift. It's farther right than TMS. Same thing happens for the carbonyls. For the carbonyls, we also have some shielding. So for instance, they use this cone terminology. Like this is what I just showed you, and then here's the cone terminology, where the plus is a shielding area, and then over here's the de-shielding area. It turns out that when you have a pi bond of either a carbonyl or a double bond or a triple bond, although the triple bond is different, you now end up with shielding here and then the de-shielding to the outside. So that's why the hydrogens then move to between 5 and 6 for an alkene. To aldehydes show up at 9 to 10. So it's the same magnetic line of force that you get from the pi bond. So that's why those peaks are farther to the left. Okay, so that's the chemical shift and why hydrogens have different peaks, positions. That'll come more into play, but we have the second thing to talk about, which is how many peaks should I expect from a compound? All right, so what we will do is we'll start at 215. Okay. So now hopefully we've seen where the hydrogen peaks show up. We have a correlation chart which you'll get for any quizzes in the final exam that shows us roughly the areas in which you'll find the hydrogens depending on what's attached to the carbon. So the next question we need to answer is, well, how many peaks should I see? And that question really should be, how many chemically non-equivalent protons are in the molecule? And chemically non-equivalent means they're different. So, what is chemical equivalence? Well, chemical equivalence technically is that the hydrogens have the same chemical shift. But that's not a helpful definition until we know how to determine whether two hydrogens are chemically equivalent or not. So here's propane in two different forms, and there's methane. One way we can do this is we can talk about symmetry functions. So for instance, these two CH3s are the same because they're basically mirror images of each other. If I put a mirror plane down the center of the molecule here, those two are the same. And then what's different is the CH2, that would be different. So in a propane molecule, the two CH3 groups would be equivalent to each other, and the CH2 group would be different. So we can use the mirror plane. We can use a mirror plane, just like this. We can use the mirror plane that way. Or for this propane molecule, the way I've drawn it, the screen is a mirror plane. So the screen cuts the molecule in half through this hydrogen, through the center of that carbon, through the center of that carbon, in between those two hydrogens, and between the hydrogen and that carbon. And so what would happen then is this is the equivalent of that, this is the equivalent of that. So in other words, these, if the mirror plane is through the center of, is through the screen, then these two would be equivalent, those two would be equivalent, and those two would be equivalent. So that's if the mirror plane is in the screen. Or if you're watching this later, through the center of your computer screen. It's like doing a podcast. We have live and we have the later live. So we do the same thing with the methane group. This kind of reminds us of what we did when we looked at chiral centers. So for instance, I could pass a mirror plane through the center of those two hydrogens, that carbon, and the mirror plane would kind of like split, and then those two would be the same because they're on the same plane, and then I could do the same thing with other mirror planes. Now the mirror plane stuff is, I think it's not the easiest way to determine if two hydrogens are actually equivalent. But I'll show you one more in terms of rotational symmetry, and then we'll go to what'll be a much easier way of doing this. And unfortunately, have you talked about free radical halogenation in Dr. Swan's class? You talked about it last semester? Yes, sadly I didn't, because that would be the next analogy I would use. So we'll make it similar. All right, next. They can be interchanged through free rotation. That's easy enough. That's easy enough to see, hopefully, if I had a CH3. If I have CH3, I can rotate this hydrogen there, that hydrogen there. So if I can rotate the hydrogens into each other, they are equivalent. So all CH3s are equivalent to each other. Meaning the three hydrogens in the CH3 are all equivalent to each other. Not necessarily two CH3s in the molecule, but the three hydrogens in the CH3 are. Okay. Now, one of the easier ways, I think, to do this is to think about, I think there's a slide. Let me go ahead one slide. And that is, here's I think the easiest way to do it. And for those of you that have talked about free radical halogenation in Dr. Juan's class, if I gave you this molecule and I said, how many unique free radical halogenation products are there? What number would you give me? In other words, if I said write all the products of adding Cl2 to this alkane, how many unique products would you write? Do you have a number? 2? So since everybody else is like, why are you even doing this when most of us don't know what you're talking about? That's okay. So here's what we do to tell the difference. Let's replace a hydrogen atom with a bromine. And let's then determine the iupatane. And then let's replace another hydrogen with a bromine and determine that compound. And if those two hydrogens, when you replace them with bromine, give the same name, they're equivalent. So let me go back to my slide that had lots of blank space. So for instance, we'll start with propane. Let me replace, let's make it CH2Br, then CH2CH3. So I'm going to replace one of the hydrogens on the left methyl group with a bromine. And let me replace one of the hydrogens on the right, CH3, with a bromine. Do those two molecules have the same name? Yes, they're one bromopropane. So that means that those two hydrogens, or those two CH3 groups, are equivalent. And because there's free rotation around the CH3s, all 6 of those hydrogens are equivalent to each other. Both sets of CH3s are equivalent. So what I like to do is I like to give equivalent hydrogens the same letter. So I would call those A. So all 6 of those hydrogens should have the same chemical shift. Now, are those equivalent to the CH2? No, because if I replaced one of the CH2s with a bromine, do I get a new compound? Yes, I now get what? 2 bromopropane, and that's not 1 bromopropane. So those hydrogens are now what I would call B. They're different. But both of those hydrogens, so if I replaced one hydrogen with a bromine of the CH2 and then I replaced the other hydrogen of the CH2, I'd get the same compound. So the 2 CH2s are equivalent. As foreshadowing to what's called free radical halogenation. If you add bromine or chlorine to an alkane, you end up replacing a hydrogen with a bromine. That's free radical halogenation. So if I did that as a reaction, I would end up with 2 possible products. 1 bromopropane, 2 bromopropane. Well, we'll get to that in my class eventually. So that's how I can tell the number of equivalent hydrogens. So what does that mean? The number of peaks in the spectrum. With each peak hopefully occurring in a slightly different chemical shape. Does that kind of make sense? All right, let's find out. Okay, so I just did this one. This one is A, B. So there were 2 sets of non-equivalent hydrogens in propane. Let's do this one. Do we have a number for that one? Don't yell out any numbers yet. Okay. I don't have your names loaded up into the spiral, into the wheel, but I do have dice. I have dice on my carpet. I don't have my carpet with me. So I have virtual dice on my phone. So 2 dice. A 3 and a 4. 1, 2, 3. 1, 2, 3, 4. More.
I got 4.
4. Let's do that again. A 5 and a 4. 1, 2, 3, 4, 5. 1, 2, 3, 4. What number did you have?
For the same one or
For the same one.
I got 4.
4? Okay, so we got 2 4s. Anybody have a number different than 4? I heard a 5 before we started. What do you have? 3. So we got 3, 4, and a 5. Any more numbers?
Wait, no.
You're taking back your 3?
Yeah, because I had like
So you got 4s and 5s. How many 5s do we have? You have no choice. It's great. You are? Yeah. So you got 4s and 5s. So you got a 4 and a 5. Okay, let's write this out. CH3, CH, CH3, CH2, and CH3. So will everybody agree that a CH is going to automatically be different than a CH2 and a CH3? So that means the C, I'll call the CHA, and I'll call the CH2B. So that's 2. So I've got 3 methyl groups left. Are any of those 3 methyl groups the same? Which ones? The one on the left is this. So this one, and the top one. So are they C? Are they the same or are they different? Same. Everybody agree with that? Okay, so the one remaining CH3, is it the same as C? No? So then that would be D. So it looks like 4. Looks like those are the 4 sets of equivalent hydrogen. Do you understand why the 2 numbers are the same? All right, I'll give you a few minutes to work on the remainders. Now, for the alcohol here, forget about the OH. We're not including OHs or NHs in this game. So for each one, how many unique sets, and can you label them as A, B, C, etc.? Just treat it as an OH group, but don't count that hydrogen. When you give me the number, don't count that hydrogen. That's 1,000. So of the remaining carbon groups, how many of those sets are unique?
when we're doing the OH, it doesn't have a hydrogen attached to it.
There's no hydrogen, there's no water. You're only labeling the hydrogen. That's why it's better to draw this first.
This one is.
I was like about to wear a hat. Yeah, if I wear it, I can like
I would recommend that. And then I would like to turn the mirror pointing to see if they're equivalent. Alright, so I hear the volume going up and not about chemistry, so everybody must have numbers. So my suggestion again is write in the groups. If a carbon does not have hydrogens, it doesn't get a letter. Okay, so there is that molecule. What do we think in terms of the total number? 3, 4. 1, 2, 3, 1, 2, 3, 4. We won't call it. 1, 3. 1, 2, 3. Lucy. 5. Do we like that? Anybody not like that? Want to throw out a different number? You have a different number?
I mean, I have 2 looking at this, so I'm going to say 2. I had 2 and 5. I thought you, I had 2 and I thought
Doesn't make me feel good.
It ain't two.
Didn't say that. So 5. So let's see. We're agreed that the CH is its own group, as is the CH3. So we've got an A and a B. What about all the CH2s? So can I pass a mirror plane through that molecule and cut it in half? Like this. So what is that going to do? That's going to make C, those two equivalent, those two equivalent, the last one maybe not equivalent. Now if I could pass a mirror plane through the molecule this way, then the C and the D's would be equivalent, but I can't pass the mirror plane that way. So it looks to me like there's 5. Does that make sense to everybody?
Yeah.
All right, let's do the alcohol one. CH2, 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 CH3. Not counting the OH. As a hydrogen, let's see, we got a 5 and 4. 1, 2, 3, 4, 5, 1, 2. 4, we already called on you. 3 and a 4, 1, 2, 3. That's the popular number. 1, 2.
Wait, I thought we were switching the OH group for like this methyl group, so.
Well, no, we're going to keep the OH group, it's just we're not going to count this hydrogen. So these groups, how many of them are unique? Of these 4 different, of those 4 groups, how many of them are unique? How many of them are unique?
There's 2 different groups. Or 3 different groups. Wait.
Keep going.
4 different groups?
She needs help.
I didn't do it.
1, 1.
No, if you put a methyl group there, you're going to get a completely different
Yeah,
number.
that's what I did.
So we want to keep the OH there, but that hydrogen doesn't count. So how many groups? Yeah,
There should be 4.
4? 4, we agree with 4? Is there any mirror plane that I can cut the molecule in half vertically? No. So that would make it A, B, C, or D. So there's 4 different groups there. The last one. I mean, notice the maximum number is the maximum number of hydrogens. But if they're equivalent, that's going to drop down the number. So what do we think in terms of a number there? A 1 is, well, we can go 2 and a 1. 2, 1. Yeah.
5.
5. Have anybody agree on 5? Yes? Any other numbers?
7.
7?
6.
6?
8.
What?
8.
Okay, 8's possible. That's the maximum. So we got a 5, 6, 7, and an 8. Any more? Now, first thing I do is look for a mirror plane. What you have to realize with the benzene ring is, let's just write this out as a group. Let's write this out. So if I could write this as a CH double bonded to a CH2. Well, that's what I've got, right? So I could write it that way. Is there a mirror plane that would cut through the molecule there? Yes? There is. So if I can cut the molecule, so if I can cut this molecule in half with a mirror plane like that, what hydrogens are equivalent? Is this one equivalent to another? Yes? Which one? This one? So let's call this one HA, HA. Is this one equivalent to another? Yes? That one. How about this one? Is it equivalent to anything? Yes, no? No? We agreed no? Because the mirror plane, if this was equivalent, the mirror plane would have to go this way. And that's not possible. So that one's going to be C. Okay, so now let's deal with the double bond. Are we in agreement that this one is D? Because it's not equivalent to anything? The CH group? How about the two carbons on, how about the two hydrogens on the end? Are they different? They're same to each other, but different than everything else? I'll buy half that. They're different than everything else. Because you can what?
You can change like cis or trans to EZ.
So these two, are they equivalent to each other? And here's how we tell. If I put a bromine here, I have trans. Right? Trans bringing bromine. If I put the bromine here, I have cis. And those two are not equivalent by rotation. So it turns out that in this case there's an E and an F. And there's no mirror plane that I can pass down the double bond. There's no mirror plane that will make E and F the same. So they're different. So how many was that? 6. So whoever said 6 was right. I mean, if you don't like that, just replace the bromine. So how would, if I put a bromine here, that would be like a 1 bromine, 2 blah 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 group. 1 bromine, 2 group, same thing. 1, 3, 1, 3. So this is the first thing we have to do, is we've got to figure out how many peaks should I see in my spectrum. Then I can figure out from that correlation table where should they show up between 0 and 12. Okay. And this is the easiest way I can do it. Like I said, sometimes when we get through free radical halogenation, it would be how many different products are there. So is everybody kind of okay with that? Okay, now, here's the 3 things. Whenever you have an NMR spectrum, 3 things will give you, or 3 things you're going to use to determine the structure. The first thing you're going to use is the chemical shift, the position of the peak on the x-axis. That's number 1. Number 2 now is what's called the integration, the area underneath the peak. The area underneath the peak is going to be proportional to the number of hydrogens that peak represents. So for instance, here is methanol, CH3OH. Which peak, left or right, corresponds to the CH3 group? Left or right? How many people say left? Is the CH3 group. How many people say right? CH3 group? Well, let's read the top again. The intensity of the peaks are proportional to the number of protons. So how many CH3s are there? How many CH3 hydrogens are there? 3. It's not a fair question. 3. How many OHs are there? 1. So which one of those two peaks is the CH3 group? The one on the left, the bigger of the two. Agreed?
What's the other one?
DOH.
Well,
Oh, well, I'll explain what that is in a minute. I'm just looking at the peaks. I'm not looking at the,
whatever.
yeah, the integration part of it. So this is the CH3 peak, and this is the OH peak. And what that means is the area underneath the CH3 peak should be 3 times the area underneath the OH. Think of GC from last semester. Right? The area underneath the peak was proportional to the amount of compound. Same thing's true here. Except the problem is, how do I get that number? And here there's no numbers given. And you will see numbers given, both in terms of just the number area. You might see this is worth 3H and this is worth 1H. That's kind of cheating. Or you might see these integration markers. So in the old days, before computers ran NMR instruments, like the little benchtop thing, the pen would run across the paper. There was what was called the integrator. Now remember from calculus that that's an integration marker. So what would happen is this instrument would electronically integrate. So this is the integration marker. It would go up here, would plateau, and then it would, every time it would take a step, that distance between those two horizontal lines is proportional to the number of hydrogens, proportional to the area. So in the old days, what you had to do was you had to take a ruler and measure the distance between those plateaus in millimeters, and then you would divide through by the smallest number of millimeters, and it would tell you the ratio of the peaks. Now, when I give you these spectra, which are generated, these are computer generated on a little tiny Mac. One of the ones that was like, here it is self-contained, one that was like this big, if you've ever seen one of those. Yeah, it was back in the day. I think it's still in my lab. I don't know if it'll work. But now I'm using for door stops. This is sad. This is such a useful computer. I count the locks here. 1, 2, 3, 4, 5, 6, 7.5 locks. And then over here, 1, 2, like, I don't know, roughly 2.5 blocks or so, if I want the numbers to work out exactly right. So if you get a spectrum, and you probably won't when we start actually collecting spectra for your compounds in the lab. But I know for one of them, I know for like the esters lab, they used to just print those and then you have to measure them with a ruler. Let the computer do what it's supposed to do, which is just give you the number. But that's how we would do it. We divide by the smallest number, and we get the ratio. So in this case, the ratio would be 7.5 over 2.5, which is equal to 3. 2.5 over 2.5, which is equal to 1. So the ratio is 3 to 1. That's the ratio. Could be 6 to 2. Could be 6 H's to 2 H's. 9 to 3. But in this case, we always 3 to 1 because we have So the area underneath the peak is important. Because the area underneath the peak will tell you is this CH2 group, is this CH3 group, is this CH group, is this CH4 group? We'll get to it. So number 2 piece of information is integration. So that's 2. Position on the x-axis, integration. The third is the most important. So here is a spectrum of ethanol. Remember I showed you that ethanol peak was really big broad peaks that Block and Purcell had measured before. I basically have the same thing here. I've got a CH3, a CH2, and an OH. If I give these letters, I've got an A and a B, and for this one, I'll give this a C. So I've got 3 sets of hydrogens. Notice I don't have 3. I have more. Now what I really have is 3 sets. Because what I have is I've got, those are one set, this is 2 sets, that's 3 sets. So I've got 3 sets of hydrogens. So, as it says up on top, because I tried to put as much words there so when we go back and look at this, it'll be helpful. Most often, as opposed to least often, the NMR resonance of protons are nice single peaks, which we call single. But they instead appear as multiple peaks in the NMR spectrum. This is called spin-spin coupling, or spin-spin split. Basically, I've taken a peak and I've split it into 4, or I've split it into 3 on the right. These multiple peaks result from the interactions of spins of nearby proton nuclei and follow a formula n+1, where n is the number of neighboring protons. Okay. So for this ACH3, how many neighboring hydrogens does it have? 2. If I ignore the hydrogen on the OH, this CH2 has how many neighbors? 3. So the number of neighboring hydrogens. Count up the number of neighboring hydrogens, put in the formula n+1, that gives you the number of peaks that you should get. And then typically OH and NH protons are not included in this, which we will discuss later. So I ignore the OH. Except in the computer-generated spectrum, it always shows the OH. But notice it's the same word. Okay, so splitting or coupling, this is going to tell us more information than anything else. Because what I'm going to do is I'm going to count up the number of peaks in that group. 1, 2, 3, 4. And I'm going to say that's a 4. 4 is corresponding to 3 neighbors. 3 peaks on the other side corresponds to that hydrogen having 3 neighbors. So notice what I'm looking at here. The integration is about this hydrogen. The chemical shift is about this hydrogen. The number of peaks it's split into is not about that hydrogen, it's about the neighbor. And so that's going to help me figure out what the structure is. Because I'm going to use that splitting to figure out what's attached to that set of hydrogens. But we'll get to it. It'll become even cooler here. Right? So that's what we're going to look at, is the coupling, or the splitting. Now, we could just remember the n+1 rule. or we can go into a little bit of detail here to explain how do we get that. I'm going to take the option of a little bit of detail here into how we get that. So, let's look at the CH3 hydrogens, which we said was, well, we didn't say this yet, but how many neighbors does the CH3 have? 2. So that should make its peak a triplet. So here's my CH3. That's my CH3 group. Now, if you're paying attention earlier, I said what groups are usually the farthest to the right? The CH3. So that makes sense. All right, so let's look at that CH3. Why is it a group? Well, how many neighbors does it have? 2. Now, those HA and HB neighbors, they're little tiny bar magnets. That's what we're talking about. But the overall chemical shift of the group is the number of hydrogens, or is the electron density around the carbon that the hydrogens attached to. Right? That's our shielding, de-shielding that we did over an hour ago. These little tiny, these 2 guys, they're little tiny bar magnets. They're not, they don't shift the peak as much as de-shielding and shielding, but they do shift a little bit. So it's like the big shifting occurs because of the carbon, the groups that are attached to carbon that the hydrogen is attached to, and now these little bar magnets are going to do it fine tune. So these 2 hydrogens, they have 2 opportunities. They could both be aligned with or against the field. Now, normally I don't pay attention whether I get this right or wrong, but it seems to me, because this was only over an hour ago, that when the electrons created a field down, that's what caused what? Shielding to the right. So in this case, I probably shouldn't have the arrow down. If I'm shifting the peak to the left, I should have the peaks up. So in both of those nuclei, when the HA and HB nuclei, when they're both aligned with the field, they create a D-shielding. Right? Because they're both aligned with, and shielding means they're aligned again. That's the shift of this right here. That's the core shift of moving the CH2, which makes the oxygen to 3.5, versus the methyl is farther away from the oxygen at 1. So the chemical shift is the first big shift. And now what I'm looking at is really tiny shifts. So if both of those hydrogens are aligned up, that's going to be de-shielding, and it's going to split sample. It's going to split the peaks into one that'll be to the left. Well, statistically, one could be up and one could be down. So statistically, they could both be up, which would cause the peak to move to the left. Or if one's up, one's down, what happens? They cancel. And so you'd have the normal, you have the regular chemical shift, and there's 2 possibilities to make that happen. And then what's the other possibility? They're both down. They are shielding. And the peak is going to be split to the right. Or split up here. Or split closer to 0. So this is nothing more than, what are your neighbors? They bolt up, they bolt down, or one of each. And since that situation can occur, I'm going to split what would normally be a single peak into 3. And that's where the 2n plus 1, the n plus 1 will come from. Because of these possibilities. So this is what's called a triplet. It's a triplet. It's 3 peaks. 1 peak split into 3 because I got 2 neighbors. And those 2 neighbors can either be bolt up, bolt down, 1 peak. Does that kind of make sense? Well, we'll get to the statistics here in a minute. Well, in a second, which are sort of with me. Nobody's head bounced off the table yet. Yes, that's normally what happens. Or some glazed over look. That I've seen way too much. Now, what about those peaks? Are they same height? Nope. Take a guess. What's the ratio of height? 1 to 2 to 1. So it's a 1 to 2 to 1 triplet because it's just based on the statistics of that combination. So the center peak is twice the integration of the wings. And notice it's really nice. It's a nice symmetric triplet, 1 to 2 to 1. And that's what happens when you have 3 neighbors. So if a group is attached to a CH2 group, it's going to be split into a triplet. So then we do the same thing for the CH2 group. So now we take our CH2 group. How many neighbors does it have? 3. So what are the possibilities of the 3? 3 up, 3 down, 2 up, 1 down. And then 2 down, 1 up. And so now there's 4 combinations for those 3 nuclei of being up or down. The one where they're all up, one where they're all down, and then the 2 combinations, 2 up or 2 down. So that gives me how many peaks? 4.
Wait, why did you put methane? But you didn't say
Because I got lazy. They're technically 1 electron, right? So you can change them all to full arrows if you want. Actually, half arrows don't work. Because that's electron, right? And we're looking at nuclides. So they all should be full arrows. I'll go back and change it later. So now when you've got 3 neighbors, the n plus 1 rule says you should be split into 4 peaks. Why? Because there's the statistical combination. And what should those 4 peaks, what should their heights be? So their areas be? 1 to 3 to 3 to 1. So when I see a quartet, and that's what this is called, this is now called a quartet. When I see a nice symmetrical quartet of 1 to 3 to 3 to 1, that tells me that peak has 3 neighbors. It really tells me I'm sitting next to a mountain. Just like the triplet tells me I'm sitting next to CH3. And so that's where the splitting comes from. Chemical shift is the big tube of electron density. These little tiny bar magnets on their neighbors, that's fine tuning. But just from looking at the peaks, I've got a lot of information. Because if I know I got CH3 next to me, that's a lot of information. That was more than we got from IR. And if I integrate my peak, then I know whether I'm a CH, CH2, or CH3 by the number of hydrogens that are in my group. So we have the N+1 rule. So the N+1 rule tells me what I have. And to be honest with you, for carbon, this is as far as we go. We could use the area ratios, we could use Pascal's triangle to figure those out. I think the Pascal's triangle is also what the coefficients of binomial expansion or something like that from that. Basically, you have a 1, then you have a 1 and a 1. So then you have a 1, then you add these two together to get 2 and 1. Then you have 1, and then you've got 1 plus 2 is 3, 1 plus 2 is 2, and then 1. That's as far as we go. For hydrogens and hydrocarbons. So here's some rules about coupling. 2 equivalent hydrogens will not couple or split each other. Protons bonded to the same carbon typically are equivalent, but they will only split each other if they're not equivalent. Okay. Protons on adjacent carbons normally will couple. That's the nature. Protons separated by 4 or more bonds will not couple. That's generally the case, but not always. We may get into cases where that's not quite right. Okay? So the world is great when you're a group sitting next to a neighbor. One neighbor. So if I'm this CH3 right here, we'll call that A. What should that be split into? Triplet? How many neighbors does it have? 2, so that makes it a triplet. So this CH3 we would expect to be a triplet. How about this CH3? What? Not a triplet. Doublet? Are we agreed? Or we still solve but anytime we do that, that's I believe it's not quite right. So this one has a neighbor, its neighbor is CH, so this one would be a doublet. That's its neighbor. It's attached to a CH group. So it has one neighbor. How about this CH3 group over here? Doublet? attached to a CH as well. Yeah, it's a previous problem with less than 30 minutes. Which now I'm going to use to say, what about those two CH3 groups? Those two CH3 groups are equivalent. They're equivalent. So what I would see is a single doublet with an integration of 6, because there's 6 hydrogens in that peak. Because those two CH3 groups are equivalent. So we can predict the splitting patterns for those ones, because they had one neighbor. What about the CH2 and the CH? Well, things are going to get pretty ugly for this CH2. Because it has what? 3 neighbors on this side, then it's got 1 neighbor on this side. So could we add those up and say it's got like 4 neighbors and it's got like 5 peaks? Yes, we could do that. We could say it's got 3 plus 1, so it's going to be approximately 5 peaks. What does approximately 5 peaks mean? Well, it means anywhere from 3 to 6 maybe peaks. Well, I might increase that to like 7. No, I'll take it 6. 6 peaks max. What? So this is what's called, when you're in between 2 non-equivalent groups, you now have a complex splitting pattern. Things are beautiful when you just have one group or when you got 2 equivalent groups. Except for 1. But when you're in between 2 non-equivalent groups, we can estimate by adding up the 2 number of hydrogens and adding up. So it's going to have approximately 5 peaks. That's probably not good enough of an explanation. So here's what really happens. To the left, it's a quartet. To the right, it's a doublet, right? If I just treat the 2 groups separately. What I really have is either a quartet of doublets or a doublet of quartets. Well, this one I can do with my fingers. I have enough fingers to actually use this example. Doublet of quartets. Right? Doublet of quartets. Now, depending on how those doublet of quartets are spaced, I can have 2 quartets. Or I could have 1, 2, 3, 4, 5, 6, 7 peaks. Or I could have 1, 2, 3, 4, 5, 6 peaks. Or I could have 1, 2, 3, 4, 5 peaks, depending on how they're spaced relative to each other. And we could do, there is 4 doublets. Same thing. We can end up with all these different patterns. That's why I say 5 peaks roughly, because it's really going to depend on the spacing between the quartets.
Higher powered magnet be able to split.
Oh, we'll get to where we want to invest money in big magnets here in a minute. It has to do with it. But that's what a doublet of quartets looks like. So when you have a doublet of quartets, you have, then there's a quartet, and there's a quartet, so if they're overlapping, they might be, you might have a total of 8 peaks. You might have 1, 2, 3, then another one, then 1, 2, 3 on the other side, which would be 7. In other words, the distance between the 2 quartets. Right? If you're watching, if you're listening and watching this in podcast mode, just imagine you're taking like each hand with 4 fingers and moving them closer to the other. I'm not going to record myself. And sometimes this would be, I've seen people write this like a 2x4 or a 3x3 if it's a triple to triplets. So this is complex. And so all we can do with our complex splitting pattern is just simply estimate. So we're going to estimate the number of peaks by using the n plus 1 rule now, where the n, we're going to sum both sides. Sum of hydrogens on both sides. And then in the end, plus or minus 2. So 5 anywhere from 3 to 7 is what you end up with. But here's the thing. If you don't see a nice doublet or nice singlet or nice triplet or nice quartet, and you see a mess of peaks, and they're nicely symmetric, it means you have this situation. If you end up with a mess of peaks that are not quite symmetric, then what you have is overlapping chemical shifts, which is a little bit different. So this is what happens when you're in between 2 non-equivalent. That's fine. That just means I'm in between 2 non-equivalent groups. I'll estimate. And if you have a computer, sometimes you can simulate this to see how many you would have. Now, isopropyl groups. Isopropyl groups are their own beast. Here's the 2 peaks of an isopropyl group. Here is the CH, and here are the 2 CH2s together. What you can see is what we predicted the other time would be the 2 CH3s are equivalent. They're each a doublet, so you have 1 doublet of 6 hydrogens, but they have the same chemical shift. That's what you see on the right. So whenever you have an isopropyl group, you always have a doublet for the methyl group. But for some reason, the CH decides that these 2 methyl groups are not equivalent in its eyes. And so what it has is a grand total of 1, 2, 3, 4, 5, 6, 7 peaks, which would be 2 3s plus 1 doublet. So an isopropyl group is always a doublet and a 7 peak, because the CH group doesn't recognize the 2 methyl groups as being equivalent. It's strange. I don't know why that happens. I've never had the ambition to look it up. It just happens. So that's an example of the CH thinking it's in between 2 non-equivalent groups, when really it is. A couple of constants. So, everybody with me so far in terms of splitting pattern? What's the most important thing to remember? N plus 1. N is the number of neighboring hydrogens. If I'm in between 2 non-equivalent groups, it's a mess. But it's a symmetrical mess, as opposed to 2 groups overlapping, which is an unsymmetrical. Okay. coupling constant. So when you have a triplet, there's a distance between each peak. And that's what's called J, measured in hertz, which is called the coupling constant. There are many reasons why the coupling constant is important. We will probably not measure a coupling constant in this. In other words, when we print out your proton spectrum, we won't actually print the distance between that, between the peaks. We could. But what's important about the coupling constant? It's the distance between the peaks in a molecule. It's measured in hertz. Here's the thing. Coupling constants are constant. They don't change as a function of the magnetic field. So if something's supposed to have a 3 hertz coupling, it's 3 hertz whether you have 60, 100, or 300 megahertz. It's constant. Coupling constant. Okay, it never changes. And the useful part of this that we probably won't get to is that if you have a CH3 next to a CH2, so you have that triplet quartet pattern that we saw earlier, if two groups are actually coupled to each other, splitting each other, their coupling constants have to be exactly the same. So if I had multiple ethyl groups in the molecule, in theory, I could measure the coupling constants of each of the triplet quartets, and I can tell which triplet goes to which quartet. Because they have to be exactly the same. So those are coupling constants. So I simplified it is necessary. You get wound up in this and you don't realize you've gone an hour and 10 minutes since the last break. So let's start back up again at we'll make it close to 3:33-ish. Because the sooner we start, this is the last segment, so the sooner we start. We'll talk a little bit about this and then start putting stuff together. All right, so 3:33, I will start talking again. Okay, so our last part here. Okay, so coupling constants. If you're gonna determine a structure from scratch, you're probably gonna use these. I'll just show you a couple cases where these values can be important. For instance, they would be important if I wanted to determine, where's my pen, if something is cis or trans. If I want to know if something's cis or trans, then the difference in the double bond is 10 and 15 hertz, easily measurable. Okay, so think about all the reactions you learned in lecture or you will learn in the next week. Friday's test, or whatever your first test is. Tomorrow, I'm going to stop early so you can study it here. So all the reactions where we said it was 100% cis or 100% trans, when we're forming a double bond, that's how we tell. Is by the NMR. We'll get the benzene rings later on because it can tell you whether something's 1,2 disubstituted or 1,3 or 1,4 disubstituted, which we'll later on call orthometal pair. So coupling constants can be useful, like in the cis-trans case. And let's see, this is the molecule I gave you earlier, and asked how many equivalent hydrogens there were. Styrene. And so if you look at styrene, you would see one, 2, 3 of the hydrogens attached to the double bond. So you would see all 3 peaks, proving that HC and HB on that chart, not equivalent, like we said, I don't know, somewhere between 15 and 45 minutes ago. Their coupling is really complicated. Like, if you looked really carefully at these two, they're like doublet of doublets. There's a big doublet, and then there's little tiny doublet. Each peak is split up into doublets. This one over here, that's a doublet of doublets. So doublet of doublets with the spacing a little bit different. So that's how complicated this can all get. The peak is 7 is the benzene ring. It's less. Not going to worry about that. And then, if I wanted to go into the gory details of my splitting trees, so what I did with my finger, I did a movable splitting tree. So for instance, if I'm looking at A split into a doublet by C and into a doublet by B separately because they're not equivalent to each other. So that's a doublet of doublets. So the first splitting would be 17 hertz, and the second splitting would be 11 hertz, and I would end up with something that looks like that. You really get into the gory details, that's what it looks like. So when I said spacing earlier, the spacing between the two quartets, that's the coupling constant. And so depending on how those are, we can get significant overlaps. Now, who cares? Well, as my NMR is slowly dying to the point of being like, we should put it out of its misery, just part of it, an expensive part. The question is, do I really need to buy next a 300 megahertz instrument that they don't sell? So I have to step up to 400 at probably $330,000. Again, got the money, so I don't have to worry about that. Or should I just spend 80 on a 90 megahertz instrument, which someone is constantly asking me to do? And I'm like, no. But what should I do? Why is there a difference? We've already seen that the peaks, the frequency of the peak will be different. But what isn't different is the coupling constant. It stays the same. So there is a fundamental rule, which somebody told me that you can violate, which I don't believe, that the distance between two peaks is in a certain number of hertz. That's the chemical shift. That's delta. That varies according to magnet strength. So that has the possibility to change. But these little coupling constants, they don't change. And so there is a fundamental rule that says, once your difference, we'll call this delta, once the change, the chemical shift change in hertz between two peaks, the difference is less than 10 times the distance of the coupling constant, your spectrum goes to hell. It actually becomes what's called second order. So these two peaks right here, wait, we did this molecule earlier, didn't we? It's almost like it was planned out. That's the quality of teaching you get here. So, this CH3 we said was what? It was a triplet of quartets. Right? Quartet on this side, triplet on the other side. So it's a triplet quartet. That's, I think, this one. Then the CH2 would be a doublet of quartets, and that's this one. And then you have the nice triplet and the doublet. We already figured that out. So this would be a spectrum at like 300 megahertz. We would see a nice 1, 2, 3, 4, 5, 6, 7 septuplet on the left, pentuplet on the right. It's symmetrical, it's clean. That's because the difference in hertz between those two peaks is more than 10 times the coupling constant. So somebody says, hey, I don't want to spend $300,000. I want to buy a desktop 60 or a desktop 90 megahertz instrument. And I say, no, not happening. And here's the reason why. And this is why I got a C in spectroscopy in undergraduate school, because I couldn't make heads or tails of this. That's what I tell myself anyway. This is the spectrum taken at 60 megahertz. Guess what happened? The distance between the two peaks is now less than 10 times the coupling constant. And so this is what's called the second order spectrum. I cannot make heads or tails of that. It's just, well, what you see is you see all the coupling trees, all the splitting trees. But this is what's called the second order spectrum. This is why we invest money in big magnets. Because if we don't have a big magnet, we cannot overcome that fundamental rule that says the only way I can spread the peaks out in hertz is to go to a higher magnet, because I can't change the coupling constant. If I've got a protein or something like that, where I've got tons of protons in a limited space, gotta spread them out, gotta go to an ion instrument. So this is what you're looking at if I was to buy a 60 megahertz, which would be like $70,000. Which, I don't see the economics in that. Now, our engineer that comes in and fills the magnet with helium, he said some guy that's written all the NMR software ever, Krishnamurti. Somehow he has come up with software that will take this and make it look like it's 300 megahertz spectrum. Apparently I have the software. I haven't tried it. I think it's one of those things that's like, it's some principle, some foundational principle of like, probably physics, that if we violate the world ends. So I don't know how he does it, but apparently he says he can do it. So this is the kind of stuff we saw as an undergraduate that made absolutely no sense. But this is the danger. We have to use at least a high enough magnet to spread things out. Otherwise, they become second order and we can't interpret them. So that's where the importance of the coupling constant being constant and the field, the distance between the peaks and hertz being changeable, comes into play. So now I get that. And that's ugly too, because the splitting trees are what we don't want to talk about, but still, I'm down to 7 peaks of that. That I can interpret. So again, another reason why we want to go to, sometimes have to go to a high field instrument. I would stand no chance of doing any biomolecules of any kind of size on my magnet, because everything would be squished together and it would start doing strange things. Okay, so let me go back. All right, rules for coupling. Coupling to non-chemically equivalent protons. I showed you that. That's like the doublet triplet or the doublet quartet. We use the n+1 rule. We sum up both sides and get an estimate. Non-first order effects. That's when they break down because the distance in chemical shift in Hertz is now on the order of the coupling constant. That's not the exact equation, but it's 10 times that. So then spectrum go bad, which we've seen. So that's why we need high field NMR instruments. Other complications to splitting, what's called fast hydrogen exchange. I've told you we've ignored the OH and NH. Why? Well, because if I have an OH group in my molecule, it could hydrogen bond to another OH molecule. So as these hydrogen bond, what happens is that when they break apart, sometimes they break apart, and I'd have to give this one like another hydrogen bond over here, but sometimes this hydrogen right here, when it breaks apart, it goes from being attached to the one oxygen, one alcohol to the other. So hydrogens are exchanging in the solution. The OHs are constantly swapping with each other. Same thing's true for NH, and same thing's true for carboxyl gases. Those are called exchangeable hydrogens. And so they're constantly switching with each other. On the NMR time scale, on my picture in the instrument, what happens is I don't see the OH attached to the same oxygen. And so what happens is what would be a nice peak begins to broaden out. So much so that sometimes it just broadens out as the baseline level. So in general, we don't know where OHs are going to show up because they're exchanging. That means they can show up anywhere from 2 to 12. And a lot of times you don't see them because they're very broadened out. The OH, NH, and C double bond OH, the way I remember that those are my exchangeable hydrogens, is those are the groups you want to keep away from Grignard. Right, Grignard is you protonate all those. So that's the group of exchangeables. How do you tell if you have an OH peak in your spectrum? What you do is you add D2O to it. So deuterium is hydrogen with a mass of 2. And so what we do is we'll get to this next week, each isotope of a nucleus has a different one-more frequency. While hydrogens spin at 300, deuterium spins at 46. Give me plus or minus 10 either way. They spin at completely different frequencies. That means that the instrument's tuned for 300. I'm not seeing 46. So if you add deuterium to your sample, the D's will now exchange with the O's, and it'll just broaden the peak out like this. And so that's how we can tell if I've got an OH molecule. So sometimes with some spectra I'll put an asterisk on it and say, this peak disagrees with each other. That's it. They never couple. They rarely ever couple to a neighbor. So they're not treated as neighbors, and we don't worry about them and the neighbors. We just don't worry about relations. So that's a complication to splitting. Okay? So those are all of our complications. I guess the one thing that I did talk about earlier was, what about cyclohexane rings? What can you tell if the hydrogen is axial or equatorial? No. Because if the ring is constantly doing a ring flip, the hydrogens are going from axial to equatorial. So when I take the NMR snapshot of it, it's just a blurry picture. So I can see a single peak instead of separate one. They still couple, but I can't tell the difference between that. Okay, so there's our coupling. Everybody kind of with me? So I've kind of added on to what I talked about last week in terms of why it's important to have strong fields, because we need to separate peaks out, the splitting with the N+1 rule, what happens if you're in between non-equivalent groups. So, great. How do we use this? Here's an example. So, here is an NMR spectrum of a butyl bromide. And your choices are N-butyl bromide, sec-butyl bromide, isobutyl bromide, or tertiary bromide. So can we figure, if somebody said, hey, here's a test tube of a butyl bromide, tell me what it is. I go, I take an NMR of it, there's my NMR. And I tell that person what they have. And if I can do this one, well, there's another one. And there's a third one. I only did 3 of them. So which one is that? Do we need help? I'm totally lost here. I'll play you. I'm totally lost. And I want to lose. So, what do I need? Yeah, I know I need help. But what specific kind of help do I need? Kevin?
I feel like you need to look at all the systems and what they actually look at. There's like 3 or 4
Okay, so I need a strategy. So what's my strategy?
look at each of the like systems and figure out what's going on.
Okay, let's look at the group of the peaks and figure out what they are. So what's the peak on the left? How many peaks are in there?
That's 6.
Looks like I got 6. What does that mean? How about it means that hydrogen is what? In the middle between 2 non-equivalent groups, roughly 5 hydrogens? Then you can wash the rest. So maybe like there's 5 total protons, but it's what we call a multiplet. When you have a multiplet means you're in between 2 non-equivalent groups. How about the other one? How about the one down here? How many peaks here? 5. What's that mean? I have another multiplet. All right, what about the peak next to it? Doublet. What does that mean? It means it's next to a CH. Let's do the last one. What is it? Triplet. What's it next to? What kind of group do you think that is? The group farthest to the right. A CH3. Do we have evidence of that? We might. But let's just tentatively call it a CH3. Okay, so want to eliminate any? Which ones? We want to eliminate the first one. Why are you eliminating the first one? Because there's no CH in the first one. And we know we have to have a CH because one of the peaks is a doublet. Okay? And the last one we're going to eliminate. So we're down to 2 and 3. All right, we just used a couple patterns to help us. How about the council shifts? Council shifts tell us anything? We're suspecting the peak farthest to the right is a methyl group. How about this peak right here? At 3. It is E shielded. So what does that mean? It's attached to a carbon that has what kind of group attached to it? What? Something that's electron withdrawing.
DBR.
So that peak at 3, that's the hydrogen that's attached to the carbon that's attached to the bromine. And it's a multiple. Everybody get that the peak at 3 is the carbon attached, is the hydrogen attached to the carbon attached to the bromine. So it's a multiplet. So is that helpful? Is that helpful in terms of we're down now to this one and this one because those two contain CHs? Well, I don't know. How about this? I like to put into groups because at this point my mind is I have a question then. So if I look at this one, what would that CH2 be? What would I predict it to be? Single, double, triplet, multiplet? Quartet, multiplet. Doublet? So that should be a doublet. But it should be a doublet at 3 to 4 parts per million. Do I have a doublet at 3 or 4 parts per million? No, so what's that leave me with? This one, what should this one be? Whoops. What should that carbon be? Singlet, doublet, triplet, quartet, multiplet. Multiplet. That's a good match. How about this CH3? What should it be? CH3 on the right end. What should that be? Single, double, triple, quartet, multiplet. You're pretty convinced it's doublet. Everybody else? What's its name? So it's a doublet. How about this CH2? What should it be? So CH on one side, CH3, so it's going to be a multiplet. CH3 here. Triplet. Does that match up with our pattern of multiplet, doublet, triplet? Yes. The peak that's attached, the hydrogen that's attached to the bromine is a multiplet. It fits that molecule. So what is this spectrum? It is that one.
Is the doublet not over-shifted because it's relatively close to the ground?
Exactly. So I've got 2 methyl groups on the right-hand side. The CH3 is closer to the bromine than the other CH3, and so that means it's a little bit more heat-shielded, and so it's a little bit more to the left than the other methyl group. Exactly. Okay. So, notice that we kind of did both approaches. Your approach was, let's look at the peaks, determine their patterns. And we eventually have to do that. But the other approach you can take is, let's look at the molecule and let's predict patterns, including what should be the peak farthest on the left. And what would be the patterns of the nuts. So if it's a matching game that we're playing, we should be able to match that. Now, we just matched the spectrum to the compound. Now what would we do? Now we'd come over here and say this one's A, this one's B, this one's C, this one's D. And so I would say, okay, that doublet, that's D. This methyl group is, this methyl group is A. This multiplet here is B. And then the multiplet that's attached to the bromine is hydrogen C. So now I'm matching the hydrogen. So there's two more. So you can apply those approaches to it. So the takeaway here is I can use the proton NMR to tell the difference between a butyl group, a terse butyl group, an isobutyl group, and a sec butyl group. And I didn't even do ethyl, methyl, or the propyl. Although we saw what an isopropyl was. Doublet and then the second. So, what was it? This is week 3, right? Only one more week left. Yay. In week 1, when we talked about infrared, I couldn't get that information. If I had ethyl alcohol or 100 chain club alcohol, they all look the same. Now I start getting that fine information. Now I can tell the difference. And so now if I start looking at this, it would have been nice if like Markovnikov would have had an NMR. Because then he could have added HBr to stuff all day long and could have figured out exactly what it was very quickly. He did not have it. He was about 100. Between 170 and 50. So this is where the power of this comes from. In terms of being able to determine what the structure is. So you've got two left. So you can see if you can apply that approach and get and make those and match up those spectra. But you need more practice than that. And we need like practice that counts. So on in the folder there is actually here's a set of there's propyls and butyls with the answer key if you want to practice these. So let's see, propyl, butyl, what's that? So there are a grand total of 1, 2, 3, 4, 5, 6, 7 petals. And then each one of those has A, B, C up through Z. Yes, through Z. Numbers of hydrogens. And then there's a spectrum with each group having a number. So your homework problems for the next week though are to match the letter with the number. for those 7 spectra. And those 7 pencil chlorides. So you can use a combination of both predicting from the structure and then looking at the spectrum. Take full advantage of the fact that hydrogens attached to carbons attached to chlorines show up a little bit less than 3. If there are no peaks in the spectrum left of 3, or in the 3 range, that means the bromine and chlorine is attached to a partner with 0 ions. If you looked at the last one, the last spectrum in this packet, it's a single peak with nothing at 3. So that tells you a lot as well. So that's what you're going to do for next week for math exams. Just write them on the write them on the paper, and then we'll collect those up next week. Okay? So if we're going to have a quiz, which I think we will, for next week, the quiz would be maybe me giving you a spectrum and saying high field, low field, high frequency, low frequency, de-shielding, shielding, which direction do those go? What changes when you have a stronger magnetic field versus what does not change? Coupling constant, chemical shift, doesn't change, remember? So those would be my 2 big things. Because I could ask you some basics on this, like is it a single, double, or triple bond, but I'm not going to ask you that until we get to that. Next week we're going to talk about non-hydrogen NMR. And we're going to put everything together, and I'll give you some spectra and say, here, tell me what it is. And then after that, experiment. But you'll still get some NMR homework along the way, because I don't want you forgetting this before you get to the end of the semester. All right, so you can take one of those, turn in your math spec homeworks up here. And if you want your quiz from today, you can go ahead, and I think they have them over there. They'll give them to you. Up here. Well, let me stop this. Okay. That means it has shielded, but it has the more single peak it has. No. That's 0 minutes. Well, CH3 attached to it. How many hydrogens are on that C? No. Oh, okay. So it has to have them still carbon. So the difference between those is they both have carbon, but one would have a benzene ring and one wouldn't. So let's see.
I got benzene ring has strong peaks at about 3,000.
It doesn't necessarily have strong peaks, it just has peaks at 3,000. So if you're looking at that, you would see, for instance, carbonyl, and then you see some peaks above 3,000. So they don't necessarily have to be strong, they just have to be above 3,000. So that's where that was.
What did you eat?
No, I have them.
Okay.
I've got them up here, and you can go ahead and
Yeah, I didn't give them to them. Because you haven't taken it, so you can't get it from them.
Oh, okay.
If you haven't taken it, it's not graded. All right, so what you're going to do is match the spectrum, and there's your truck.
Okay.
All right, I'll see you tomorrow morning.